Okay, calculus, welcome back. We're going to be talking about particle or projectile motion. Talking about projectile motion some more. So this is just going to be projectile motion part 2, or particle motion part 2. Now I'm just going to work through an example problem, and then the next lecture is going to be talking about displacement, which is kind of a cool idea, particle displacement. So projectile motion, we're just going to be working through some examples, or one example in particular, but I want to go through it in detail, and hopefully you guys can understand exactly what's going on. So this is going to be a similar example. So this time we're talking about standing at the rim of the Grand Canyon. So Grand Canyon, very, very deep. There's some water that goes through the center of it. Okay, and so here you are, and you've got a rock. And you drop your rock. You're wondering, okay, so the question is, what is the equation for the position of the rock, or the height of the rock, with respect to time? WRT is with respect to time. So basically you're trying to solve for x of t. I'm going to put AKA, also known as solve for x of t. Okay, so the only piece of information you're really given is the height of the Grand Canyon. Okay? So you know that, or you know how deep it is, right? So I know it's not 100% to scale. The Grand Canyon, very, very deep. It's 1,800 meters, at least the point that you're dropping your rock in. So you drop your rock in, 1,800 meters. What is the equation for the height of the rock? And then you can also figure out how long is it going to take for the rock to hit the bottom, right? And that's really what we're kind of looking for. How long, right? Because that's a cool thing. It's like, if I drop this rock, how many seconds before it hits the bottom? Okay, assuming we're not taking into account things like wind resistance. Okay, so I know that the height, so x, I'm going to put initial height is going to be equal to 1,800 meters. I also know, if I think about the problem, and this is where I want you guys to I urge you guys to start thinking about these problems with a little bit more clarity, is you also know what the initial velocity is. It wasn't given to you explicitly, but you're standing on the edge of this canyon, and you're not throwing the rock up, you're not throwing the rock down, you're just dropping it. So the initial velocity is going to be 0 meters per second. You also know that the acceleration due to gravity since here we're talking about meters and meters per second, and we needed the acceleration due to gravity in meters per second squared. In this case, it's going to be negative 9.8 meters per second squared. This is another one of those numbers you need to have memorized, and it shows up all the time. It will be in your college physics classes, it will be in your college engineering classes, it will be in your college math classes. The acceleration due to gravity is negative 9.8 meters per second, which is also equal to negative 32 feet per second, which is the problem that we were working on before, feet per second squared. Okay, so with this initial information, this is what we're going to be able to use to solve this problem. Okay, so once again, I know that the velocity with respect to time, so let's chunk it up into two problems. The velocity with respect to time is going to be equal to the integral of the acceleration with respect to time. The acceleration function integrated with respect to time. So here we go. Let's go ahead and plug this in. So instead of before it was negative 32, here's just negative 9.8. Right? It's not going to change in time. The acceleration due to gravity is constant, which is nice. It makes these problems easy. So negative 9.8, when I integrate that, I'm just going to end up with negative 9.8 t, right? I'm integrating with respect to t, plus, of course, there's a constant. Now, in order to get rid of this constant, I'll call it C1. In order to get rid of this constant, or at least to solve for what it is, I need the initial condition, in this case the initial velocity. So here I can say V sub 0 is going to be, I know what my initial velocity is, it's 0. So V sub 0, I'm going to plug 0 into my equation, negative 9.8 times 0, plus C1. All I'm doing is, everywhere there's a t, just plugging in a 0. And this is going to be equal to 0, because remember, the initial velocity is 0. We drop the rock. It's not going up, it's not going down, it has an initial velocity of 0. So this goes to 0, and then I notice that C sub 1 is just equal to 0 meters per second. In this case, it's going to be meters per second, which is totally fine. So my V of t, my brand new always V of t, is going to be negative 9.8 t, and then plus C sub 1, but I'm just going to ignore that because C sub 1 is 0. So I can just say it's negative 9.8 t. Now I need to figure out what my position is. Now position x of t is going to be equal to the integral of V of t dot dt. So I'm going to go ahead and plug in and just keep going. Negative 9.8 t. This is an easier integral than the one we did yesterday because there's no constant, there's no second term. So the integral of negative 9.8 t dt is equal to, so I can say negative 9.8, this is going to be t to the n plus 1, or 1 plus 1, which is 2, over n plus 1, which is 1 plus 1, which is going to be 2. Plus, of course, I've got another constant, plus C2. So I'm going to simplify this just one more step and say negative 4.9 t squared plus C sub 2. Now, I once again need to figure out what my C sub 2 is to figure out what the whole height of the rock is with respect to time, or x of t. So once again, I go back up to my initial conditions, and I know the initial height is 1,800 meters. So I can say x of t, or x of 0, the position at 0, is 1,800 meters above the ground. Right, I'm at the rim. X of t is 0, which is going to be negative 4.9. Once again, everywhere there's a t, I'm going to put in a 0 squared plus C2 is going to be equal to 1,800 meters. Now 4.9 times 0 squared is just going to be 0. And then I know that C sub 2 is going to be equal to 1,800. Fantastic. Now I can find my general form of the equation x of t. And this is going to be equal to negative 4.9 t squared plus 1,800. Awesome. This is going to be my position, my height of this equation. Now the second piece of information that we need to solve, or that would be nice to solve for, is what in the world, how long does it take before the rock hits the bottom of the Grand Canyon, right? So taking this equation that I had, I can use this equation to solve for all sorts of great information. I'm just going to rewrite it here. And I'm trying to figure out how long before it hits the bottom. And so I know what is the thing you need to think about, the thing you need to ponder is, what is my position, what is the height, this x of t, when it hits the ground, right? Well, it all depends on where you set your reference point. I said this is going to be 1,800 meters, right? And I'm going to say the bottom of the Grand Canyon is 0, right? So this is going to be 0 meters. This is going to be 1,800 meters where you're standing. So this is going to be 0. So when, I'm basically asking, when is x of t going to be equal to 0? So all I'm going to do is replace x of t with 0 and solve this equation for time. Remember, that's what I'm trying to solve for, is how long is this going to take. So I've got negative 4.9 t squared plus 1,800. And so now I'm just rearranging this equation using algebra to solve for t. How long is it going to take in seconds, right? How many seconds? So I can add 4.9 t squared to both sides. This goes away. And I just end up with 4.9 t squared is going to be equal to 1,800. Now, next step in algebra, you guys can figure this one out as well. So divide both sides by 4.9. So divide by 4.9. Divide by 4.9. And this is going to be equal to, I get t squared, that goes away. It's going to be equal to 367.35. Now, what would the units be here? So time is in seconds. So it's going to be seconds squared. So in this case, the units are going to be seconds squared. Now, this isn't my total answer. It's not going to take 367 seconds for it to hit the bottom, but t squared is going to be 367. So in order to find the answer, I need to continue on with my algebra. I need to take the square root of both sides. And so then I just get t is going to be equal to square root of this is 19.17 seconds. Great. Now if you guys want to remember, every time you take a square root, it should be a plus or minus. But minus time doesn't make any sense, right? Because the moment we let go of the rock, time is always moving forward, right? Time's not going to move backwards in this example. In most cases, it very rarely does. But check it out, right? So you're standing on the edge of this cliff in the Grand Canyon, right? And you drop this rock, and just with math, with a little bit of calculus, you're able to figure out how long it's going to take before the rock hits the ground. Pretty cool. Awesome. All right, we'll continue on with more problems like this in class tomorrow, guys. Particle motion, projectile motion, super important, super fun. Lots of cool problems you can do with it. Lots of great information you can get. I'll sign off there tonight. I'll see you guys in class tomorrow.